Good afternoon, everyone, and welcome to today's ECA Learning Zone webinar. Today we are with our guest presenters from ECA Commercial Associate Eaton. Your presenters today are up on screen there on webcam. We have Tristan Bevan, Field Product Manager, Team Leader, and Andy Farley, Business Development Manager, both from Eaton. Just before we start today's presentation and I hand over to Tristan, just to let you know, you should see a question mark button on your screen now. Do please make use of this throughout the presentation to submit any questions you have, and we'll get to those in the Q&A at the end of the presentation. And finally, from me, today's session is being recorded, and the replay will be hosted on ECA's YouTube channel, along with all the other replays of all of our Learning Zone webinar series. That's at youtube.com/ECA Live. Now, today's webinar is CPD accredited, so to everyone who's with us now on the live broadcast, you'll be able to claim your CPD certificates through a link that will be sent to you by email after the presentation. That will be at the email address that you use to register for this webinar. So that's enough from me. And now over to Tristan and Andy for the presentation.
Brilliant. Thank you for having us here at the ECA Learning Zone, and I'll obviously now take you through our CPD on SF6 free and the benefits of. First, before I do that, I would like to just dwell on a bit of a brief introduction on Eaton, and probably best if I start by introducing myself and my colleague Andy. I'm the PDC or Power Distribution Components Field Product Manager for the UK. I'm based in the UK and joined the company in 2009, and having held several different positions within sales and marketing, first starting in our life safety division and moving over to our power distribution division. Andy himself has been here even longer than myself, and I think he started in 2001 now, and he's held a number of sales and technical roles during that period. And prior to that, Andy worked for Delta PLC for a number of panel builders and in the UK in similar technical sales roles. So please feel free to ask us questions as we go along, and we'll try and answer them at the end. Eaton is a truly global company, doing business in around 175 countries worldwide. Our global manufacturing capabilities ensure us to move quickly on urgent needs or increased demand. Local Eaton services and support teams provide swift responses that are needed to maximise productivity and uptime. The world's attention is focused on these critical needs now to mitigate the damage of human activity on the planet and to ensure a future for our children. That means helping the world become more energy and water resilient, use power more efficiently, and transition to a sustainable energy source and build a circular economy that reduces what it takes from the planet and limits what we put back into it. Our roadmap to achieve carbon neutrality by 2030 includes shifting to a low carbon resource efficient economy, and that's through supporting the energy mix, through energy storage, vehicle electrification and greenhouse gas reduction. Also through things like building and developing more sustainable communities through more resilient infrastructure, emissions reductions, water and waste treatment, and sustainable transport. And to comply with all the regulations and disclosures and the expectations around that, and to innovate to align those to the regulations required and limit our use on hazardous materials. We're a dedicated manufacturer of excellence and provide innovation solutions to make our customers more successful. Our broad array of products and services protect these people and assets both physically and digitally in this world, while improving this productivity and making more efficient. The health of an entire power system is critical, and we must ensure that all parts are working together, from the incoming utility feeds to devices and equipment that consumes that power and everywhere in between. We also help our customers meet those stringent codes and regulations, and we do more than just distribute that power now. We provide more clean, safe and reliable power from critical applications to all users. Eaton has been manufacturing medium voltage switchgear, SF6 free switchgear, for over 60 years now, so this isn't new technology to us when we come to talk about it. Before I go into that, really, I should do a little bit of an explanation on actually what is SF6 SF6 is a human-made gas that has been around now for over 100 years. It's part of the F gases, which are a range of chemicals involving fluorine, which have been used for a variety of things, including manufacture of shoes and tennis balls in the past, and even windows, and is a coolant in refrigerators. It is known as a superior, it is known for its superior properties as bielectric insulating medium, providing electrical voltage breakdown and explosion hazards. SF6 is widely used in the electrical industry to prevent short circuits and accidents, and when as an interrupting medium, SF6 is able to quickly quench an arc. It is non-flammable, non-explosive, colourless, odourless, and non-toxic. While CF6 is non-toxic, it does not support life and can cause suffocation. We will discuss more about the human implications of SF6 later on in this presentation, but heavy-duty switching operations can generate harmful byproducts from the decomposition. It makes a hugely effective insulation material for medium and high voltage electrical installations, and SF6 switchgear falls under 3 categories: closed pressure systems, controlled pressure systems, and hermetically sealed systems. The increase of SF6 in the use of electricity is due to the rise of electrification, due to economic growth and ongoing sector coupling. With a move towards mixed power sources, and particularly when we're talking about renewable energy, and becoming less reliant on those coal power generations of the past. The UK has seen a massive increase in the grid connections and rise in switchgear and circuit breakers, where SF6 is being used more widely. Across the UK network of power lines and substations, there are around 1 million kilograms of SF6 installed, and global install base of SF6 is expected to grow by at least 75% up to 2030. So there's a massive increase still going on. With SF6 so suitable for electrical switchgear and apparently harmless because it's non-flammable, non-explosive, it's colourless, odourless, and non-toxic, why should we consider alternatives? Well, for a start, operations can generate byproducts which are harmful to humans. When heated above 3,300 degrees, it becomes toxic byproducts are formulated: HF, S2, F10. During switchgear operations, aging maintenance and end of life, there is potential for adverse impact in global warming, and ongoing maintenance costs and end of life costs are incurred using SF6 switchgear. We'll discuss these implications over the next few slides. Let's have a think about the environmental considerations first. So due to circuit breaker mechanisms using SF6 switchgear, there will always be SF6 leakage. Leaks inside the tank can happen when seals fail. They can also escape into the environment during initial filling and the end of life. And SF6 recycled at the end of the life of the switchgear is costly, and leakage can occur when recovering these gases. Regulation stipulates that switchgear containing significant volumes of SF6, so that's over 6 kilograms, must be monitored and leakage rates must be reported. Although newer switchgear leakage rates are probably 0.1% per year, there is still a high number of older units with higher leakage rates and are deployed in the field. This is a major issue for humans and also for the environment, particularly when we're talking about this global warming. This table here demonstrates the global warming potential impact of gases. Carbon dioxide is the benchmark, so 1 kilogram of carbon dioxide equates to, surprisingly, 1 kilogram of carbon dioxide. There are a number of harmful gases included in the list, but if you look at SF6 at the bottom of the table, you can see that 1 kilogram of SF6 is the equivalent of 3,500 kilograms of CO2 over a 100-year period. So it significantly impacts when we're talking about global warming. As discussed previously, leaks can occur in SF6 switchgear, and these are broken down with a typical leakage of 15% during the life cycle, 5% of those emissions during gas production phase, 4% leaks when the switchgear is manufactured, 0.1 during transport and commissioning, and 4% over the lifetime of the switchgear, assuming the switchgear leaks at that 0.1% per year over its lifetime of around 40 years. Then you have 0.5% during inspection and maintenance, and then end of life there's a further 1% from the switchgear, and then 2% from that extraction and recovery of the SF6 from the switchgear, and 0% during the collection and transport of that at the end of life of the switchgear, which has a significant impact based on larger systems as well. Then we've got to think about the human consideration here. SF6 can create toxic byproducts when exposed to spark discharges, partial discharges, switching arcs, failure arcing. SF6 decomposition byproducts can take the form of gas, some of which are odorless, or powders. Other types of contaminants can include moisture and air from handling or leakage, dust and particles from mechanical generation. If byproducts are ingested or inhaled, they can cause eye, nose and throat irritation, pulmonary edemas and other lung diseases, skin and eye burns, nasal congestion, bronchitis and rashes. The table here highlights the toxic byproducts that can be formed by SF6. The main one to watch for is S2F2, which we mentioned earlier, which is odorless in its pure form, but its toxicity is on par with Frozigen, the infamous chemical warfare pulmonary agent used in World War I. The highlights some of these potential hazards of SF6 switchgear and the severity of the byproducts formed by them. Now I'm going to pass you over to Andy.
Thanks, Tristan. I appreciate that. Afternoon all. Yeah, Andy Farley. I'm Business Development Manager for Eaton for Technical and Specification Sales. We'll take a moment now to look at a survey that Eaton recently commissioned of over 2,000 adults to understand their perception and understanding of SF6 and its use. So these are the results, and the main point being that consumers are concerned about SF6. I think everybody's got environmental concerns at the moment, and consumers indicated it would be less likely to shop with the brand if they were aware that they were reliant on SF6 technology. So maybe if you were considering putting a LinkedIn post together that had you installing a SF6 filled ring main unit, it might not generate the positivity that you think it would. Yeah. So there's a big concern as environmental concerns grow. So if we look at some of the regulations now, and the EU are at the forefront of this. Yeah. So back in I think it was around 2020, the technical report that was raised by regulation 517-20141 of the EU concentrated on fluorinated gases in the UK and assessed whether cost-effective, technically feasible, efficient and reliable alternatives existed to make the replacement of fluorinated gases possible in new medium voltage switchgear. So the technical report focused on new medium voltage primary and secondary switchgear systems with higher voltages, as well as the use SF6 use within generator circuit breakers. The report does not consider retrofitting existing switchgear and other equipment related to switchgear. It just purely focused on technical and feasible alternatives. It also considered that where SF6 free alternatives are more costly than switchgear containing SF6, government or policy intervention would possibly be likely to trigger a transition. So I think we all know sometimes how conservative the electrical industry can be. Yeah? So as part of the European Green Deal, the Commission recently completed a review of the EU rules on fluorinated gases, and F-gases in medium voltage switchgear will be banned from 2030. I think it's for systems up to 24 kV. I think there's a little bit of grace beyond that for 36 kV systems. But the UK has not declared if they will follow the EU, obviously post-Brexit, and we are awaiting updates from DEFRA, who is the responsible government agency. So switchgear is a combination of switches, fuses, or circuit breakers that control, protect, and isolate various types of electrical equipment or electrical circuits. The report distinguishes which switchgear, based on voltage levels, electricity network fault levels, insulation medium, and switching device mechanisms. And for voltage levels, the report follows the convention of IEC, which varies slightly from what we see in the UK. Yeah, so low voltage, I think everybody agrees that low voltage is for voltages up to 1000 volt AC. We use in IEC world, they use the terminology of medium voltage for voltages between 1000 volts and 52,000 volts. In the UK, we would probably call this HV if you look within the regs. In IEC world, HV is actually voltages from 52 kV up to 150 kV, and EHV, or extra high voltage, in IEC world is for systems above 150 kV. So the equipment is classified by where it's used: electricity transmission lines or distribution lines. Transmission refers to transportation of large amounts of electrical power, typically on EHV voltage levels over long distances from power plants to substations. And distribution equipment is for the delivery of electrical power from substations, typically to the consumer. So at the distribution level, it's also divided into primary and secondary distribution. Primary distribution switchgear is the interface where the transition network would perhaps terminate in, say, a dedicated substation or e-house. And the environmental parameters within that building are typically controlled, or in that substation are typically controlled with like air conditioning or anti-condensation measures perhaps. And then secondary distribution is the interface with typically lower system network voltages and the link to the final customer. So it might be an MVLV distribution transformer, maybe mounted in a yard somewhere with some switchgear located nearby. In the past, maybe close couple ring main units that at the moment are only available in SF6 variants, might be used to be outdoors, like a really with a unit style of transformer as a really compact substation. And the dominant type of switchgear in public networks on secondary distribution is commonly called ring main units. Yeah. So when we take a look at some alternates. So the alternates that are available are different insulation mediums. You've got air, you've got gas, and you've got solid or liquid use as an insulation medium. Gas insulated switchgear or GIS systems typically use SF6 as the insulation medium. SF6 free gas insulated switchgear uses a gas which is a mixture of natural gases such as technical air, which is a mixture of nitrogen and oxygen, or also CO2 is used. And then air insulated switchgear systems uses ambient air as the insulation medium, so no special mix or blend. It's the natural air that we all breathe every day, with the air being the physical dimension. It takes into account the physical dimension of the switchgear. So it's because the dielectric isn't as good as natural air compared to some of these systems. They can be relatively larger, typically at that 36 kV level upwards. And then solid insulating SIS systems, or solidly insulated systems, or LIS, liquid insulated systems, use state-of-the-art designs to combine solid insulation with air at ambient pressure in a sealed tank, and also can be seen as a type of gas insulated switchgear, because the air that we breathe is gas. Yeah, solid insulation systems or liquid insulation systems may use oil. And if you look, Eaton US manufacture oil immersed switchgear still, so it's not uncommon and still used by some of the DNOs today. So if you take a moment now to look at the switching medium, we've got a choice of vacuum or SF6. So the switching devices protect the equipment from damage by interrupting the electrical current flow after a fault, or after it's detected, or after an open command. And the two devices exist, either circuit breakers or low break switch. So a circuit breaker is designed to open and close faults. So either open a fault where there's significant arcing, or close to a fault. And low break switches are purely just designed to break load, nor are they fault make. So there's a couple of subtle differences in the construction internally of the vacuum bottles, perhaps, and also a couple of constructional differences as to, within the SF6 system. be that product be deemed as a low break device or a circuit breaker device. So if we look now at primary distribution levels, so these are sort of on the energy network. These may sit behind various substations. You might get one panel with 20 feeders, and that might be feeding out to 10 different ring main systems, where you've got 2 legs for each leg of the ring. So SF6 free medium voltage equipment is widely available at the primary switchgear level and has been available for over 60 years. And there's a growing number of SF6 free solutions continually being developed for the market. Physical dimensions, technical life and reliability are identical to equivalent solutions that contain SF6. Current breaking is achieved by vacuum circuit breakers, which are SF6 free in both air insulated and gas insulated configurations. And the costs of upcoming SF6 free solutions is equal to or just marginally higher than SF6 free equivalent containing equipment. And that, well, it's slightly higher. It used to be a lot higher 20 years ago. It's come down a lot, and it's nearly equal, and it's equal in a lot of instances, and the gap is reducing all the time. But total cost of ownership is a lot lower, as we'll talk about in the end. If we look at now what's available for secondary distribution market, so these are maybe the more local substations that ECA members might be more familiar with, where there's maybe a lot, HV side on one side of the wall and low voltage consumer side. We've got SF6 free solutions. Currently, SF6 free systems are still the dominant technology. There's a lot of there's hundreds of thousands of SF6 filled ring main units on the UK market still. Commercially alternative SF6 free products are available up to 24 kV in a similar footprint, up to 36 kV in an increased footprint. And with primary systems, as we saw with primary systems, the dimensions, technical life are very almost identical to the incumbents. There are more and more manufacturers focusing on this area, and a full range of products are becoming available. Yeah. In some cases, it still remains difficult to replace SF6, maybe due to spatial requirements, or if it's a brownfield site, you maybe replace an existing switchgear. It can have some challenges, so additional consideration is sometimes needed for maybe retrofit applications. It's a lot more easier on greenfield sites, as we probably know, with a lot of installations as well. And vacuum circuit breakers are the most common alternative to SF6 on the market today. It's easier to install SF6 free equipment into sort of containerized systems. We've got a lot more control over how the internal arcing is channeled away from operators as well, to keep operators safe. If we look at the HV or the EHV level now, so we're on IEC world now, so there's not many viable commercially available operations. There's a lot of testing going on, and there's a lot of I think there's a lot of nervousness. I think the higher you move up the voltage level, the more confidence people want within the switchgear. At EHV level, if you get things wrong, entire cities or entire swathes of the country would be off. So a lot more nervousness in trialing these new alternates. So gas insulated switchgear up to 145 kV have been demonstrated with SF6 free blends, gas blends, with some successes. Commercializations expected and wider adaptations expected in the next couple of years for these type of systems. Solutions for systems up to 245 kV are going to be piloted in the next couple of years, and it's expected maybe commercial solutions may be available in next 5 years, 5 years time perhaps. So at these higher voltage levels, there's probably no getting away from it in the short term. Yeah, development of alternatives is ongoing, and there's various players in that EHV market all jostling for position as to who can come up with the optimum solution. In space restricted environments, gas insulated designs based on fluorides may be the only current viable alternative to SF6. So still a lot of issues and technical challenges to overcome at the higher voltage levels on the grid. Yeah. If we look at SF6 alternatives for equipment related to switchgear, so SF6 is used as a process gas in the manufacturing of MV instrument transformers and capacitors, and it's currently unavoidable because of that manufacturing process, with potential alternatives not delivering satisfactory results. So, you know, we may never reach a full SF6 free future because of some manufacturing processes, which really makes it more of a driver for the rest of us to get it off our networks and get it out of our systems. For equipment such as bushings and gas insulated lines and gas insulated bus bars and bus ducts, alternatives could become relatively available in the next 5 years, similar to maybe the EHV penetration and alternate use. So next steps for consideration. The technical challenges are the first major obstacle to overcome with the eventual elimination of F-gases in switchgear. The technical reports have detailed that cost-effective, technically feasible, energy efficient and reliable alternatives exist. However, where SF6 free alternatives are more costly, we probably are still going to need that government intervention. You know, I think most clients will quite happily take a saving off you and might not actually know that really in reality it's going to cost them a lot of money to maybe mitigate that product in 40, 50 years time. So it's important that everyone has their say, and the Commission's started a public consultation. DEFRA also will be opening some consultations soon as well, so hopefully the ECA will perhaps maybe do some lobbying on behalf of the members. Eaton invite everybody to maybe participate in that, because we think it's an important step, you know, as we drive towards an SF6 free future. Yeah. So if we take a look at what it might look like at a product level, here we've got a system. This is a system for use on networks up to 24 kV, rated up to 630 amp, and fault levels up to 21 kA. This system uses a seal for life tank, where all the primary switching parts, all the primary mechanisms are in a seal for life tank. Can we just move on to the next slide, please, Tristan? Thank you. By means of the seal compartment, the primary parts are all free from external environmental influences such as moisture, dust, animals or insect influences. This particular product, all the dielectric testing was done with this seal tank breached. So even if the tank was breached, you could still actually switch this and take it out of service and then ring the manufacturer for advice. If we take a moment now to look at the vacuum bottle technology. The vacuum bottles are seal for life systems. You have a fixed contact arm and a moving contact arm. Really reliable devices, rated up to 30,000 operations. So it's simple in execution. We can use the vacuum bottle in series with fuses, which is a costly, which is a low cost protection function. And then when we start to introduce, these in conjunction with advanced self-powered relays, you can get indication of contact burn, etc. as well. Yeah, it's got very low grid losses, and it's a maintenance-free system. If we take a little cutaway now of some SF6 free ring main unit, you can see here you've got a cutaway that show all the primary cables coming in from the bottom. Across the top, where you've got the wine-coloured panel, is where all the switching ports are, and to bring the vacuum breaker in or out of service, and to earth the cables down. And on this particular product, note number 5 is where you see we've got some viewing windows where you can actually view the contact arm position, and you can also see what position the service or the disconnector switch is in as well. As is common for SF6 free systems, there's extensive use of other mediums as well, such as solid insulation. So if you've got extensive use of single phase insulation, you are minimizing that internal flashover risk between phases. And also by looking at smarter designs what we call electrical field control, where we might put nice rounded edges on busbar systems, which means we can get a more compact busbar design as well. So these are common features that you'll find across all manufacturers' SF6 free air insulated systems. Yeah. One of the other benefits that SF6 free systems give us is we have 2 points of isolation. So here you can see at the bottom where you've got the cable, that denotes the vacuum bottle. That's now in the open position. And then we've also got a second open point from the bus system, where this now, the service selector switch is in the earth position. So if we were to follow this through, the next logical step in this scenario would be to close the vacuum circuit breaker, thus earthing the circuit cable down, or earthing maybe the transformer down. Yeah. So I'll hand back to Tristan. Thank you.
Thank you, Andy. Some interesting stuff there, and I'm just thought whilst we're on this, we'll show a kind of total cost of ownership here model with CapEx as the same equivalent SF6 free switchgear model. As we discussed earlier, although there may be a slight difference in cost to the SF6 free variant, due to the lack of maintenance, reduced losses, end of life cost, and the total cost of ownership is a lot more favourable for these systems. This is a utility-based model here we've got. There is a model available on the website to get a bit of an understanding, but you can see there's a significant euro saving there on the total cost of ownership.
I think that was installed based on about 1,000 units. Yeah. One of the big savings is because on systems that are air insulated at 1 bar pressure, yeah, there's no pressure gauge on the unit. Yeah. So there's no need for an annual gas check. You know, shoving an engineer in a van to go and check a gas gauge is not good use of the engineer's time, nor is it good, you know, it's not good environmental reasons, vans driving around, etc. Just to check a gauge, which is required because, you know, we need to control SF6 and leakage of. So that's one of the big key savers in this as well. Yeah, yeah, leaving the engineer free to actually do the engineering work rather than check stuff. Yeah.
And again, you know, you can take that model and say, okay, what happens if the capex is 25% additional? Well, actually, over the total cost of ownership for the life of that product against its equivalent, you still find that there is a significant reduction in that overall cost when we modeled that on a base comparison with the 25% increase for the SF6 free variant. However, as Andy did say, now you will find that these SF6 free variants are coming down in price as the technology continues to improve.
Yeah, and end of life is a big one, isn't it? You know, it's expensive now to mitigate SF6 at end of life. You know, nobody knows what it's going to. Well, nobody knows what it's going to cost in 30, 40 years to get rid of it. Yeah. At the moment, you know, it's probably cost neutral or cost minus really to decommission an equivalent SF6 free system. You know, the vacuum bottle is made of copper and alloys and ceramics, which are all fully recyclable. The cast resin is fully recyclable. The steel that it's in, you know, there's a few bits of plastics that again are recyclable. So I think it's it's about 99% recyclable, the one we've got, or the similar systems, yeah.
Yeah, no, absolutely. Wonderful. Well, thank you very much for your time today on this. I appreciate you spending some time doing the CPD. I'm going to open it up to questions now, should anyone have any, and we can answer those here, or obviously you can leave those after and we can always come back to you.
Thank you very much, Tristan and Andy, for that great presentation. Just before I jump into the audience questions, where can we contact you for more information? Where can we find out more about Eaton's work on SF6 free switchgear?
If you head over to eaton.com, there is a plethora of information over there relating to our F6 free offerings on our switchgear, and you'll be able to download white papers on the subject also, and other lots of great content on there relating to this, and there are some webinars on our website available too.
Perfect. So I'll jump right into the audience questions. First one here, what proportion of SF6 leakage comes from MV switchgear?
Yeah, that was, yeah, go watch that slide, I think.
Great question. I wouldn't be able to answer it without getting the figures for you right now. I would suggest that it would be if there's 15% at the end, 15% over the lifespan of that product, then I'd have to understand how much MV switchgear is out there to give you those figures. But we do take that data from a number of sources, and if I look, I'm sure we got a lot of that data from a number of papers on safety and design, plus evaluations of SF6 leakage from electrical networks in Great Britain. So I will have a look on that, and I will certainly come back to you on that one, just to understand what is MV and what is HV and EHV, sorry.
Okay, perfect. I can't see any more audience questions at the minute, so if you do have any questions, do submit them now. Otherwise, you'll be able to get back in touch with Tristan and Andy after the webinar for any questions. Before I wrap us up for today, just to say that if you're an ECA member, on the My ECA section of the ECA website, you should be able to find some guidance notes, technical bulletins on SF6, bits of work that we've done as ECA, some in collaboration, of course, with you guys at Eaton, and alternatives to SF6 as well. So make sure to check out your members area of the ECA website for that information and guidance. Let's leave it there, guys. Thank you so much once again for joining us today on the Learning Zone, and thanks to everyone in the audience for joining us. You will receive a link within the next couple of hours by email to download your CPD certificates for today's presentation. And yeah, with that said, thanks everyone, and have a great rest of your day.
Yeah, that's great. Thanks for the opportunity.
Thanks, guys. Cheers.
Yeah, thank you. Thank you.